Here's the last video in this series, okay? And I didn't do a sixth one because I think you can figure that out. When you get to the sixth one, the trick is just to think about how far has the cable been pulled. Okay, so think about that. What's the work in the situation when the cable's been pulled a certain distance? Okay, so that's your big clue, your big hint on that one. In this one, we have a block. It's going downhill. It's a smooth plane, so there's no friction. We're looking for a stopping distance S. Okay. We have some initial position here, and it's got a certain speed here. Okay. So what I'm going to do is, let's just kind of get a good picture in our mind here. So when it stops, it's going to be down here somewhere, okay, and it will have slid down some distance there. Now I'm going to call that SF, okay, and but the final distance here is going to be whatever that is, SF plus where it started. Okay, so I'm kind of like setting up my the beginning of my coordinate system. Okay, I'm setting my origin there, just like that. Okay, and so let's think about what we've got for forces. The spring is going to be pulling back this way, Fs. Okay, so it's going to be trying to reduce the kinetic energy. F, obviously, here is going to be trying to increase it. We also have the parallel component of the weight in there. Here's our perpendicular component for the weight and the normal force. Now, since there's no friction, we don't actually need the normal force. So we can just work with the spring, with the parallel component of the weight, and with that 100 Newton force that's acting for us there. Okay. Okay, so set up our master equation again. Okay, and I think this is going to be easier to work probably by thinking about the parallel component of gravity on the plane rather than potential energy. So we'll just do it that way. We won't worry about that term. All right, and we're starting from a certain speed, 5, okay? So 1/2 m. Okay, and now our work, let's think about what's happening with the, oh, I forgot, we got to have the potential energy of the spring. So we do need that in there. Okay, so we got minus 1/2 k, and then it's going to be SF squared minus S initial, which is actually 0. We're going to put that in a second. Okay, and then the work, I've got these two other forces. So I've got SF times the parallel component of the weight plus SF times the that force F, which is 100. Okay, so they're lined up. They're constant forces. I don't have to do any integrals or anything. I could just say it's the force times the distance, and we can call it good. Okay, just like that. Now, let's get rid of some things. All right, so for example, we are not stretched when we begin, so that term's 0. And at the end, we want the block to stop, so that term is 0 also. Okay. All right. So we've got 1/2 m vi squared. Get your minus sign on there. Minus 1/2 k sf squared. And then plus sf mg sine of 30 degrees plus f is 100. So that becomes 100 sf. Okay. There we go. We know the initial, well, let's go ahead and get our numbers on there. Okay. So this becomes minus 1/2. It's a 10 kilogram block. My initial speed is 5. And then we got minus a half by 200 newtons per meter, SF squared, which we don't know, plus SFM, 10 kilograms, G, 9.81 meters per second squared, sine of 30 degrees. Oops, I got to roll over a little bit here, and then 100 SF. There we go. Okay, so it's kind of yucky looking, but it's a lot of numbers. The only thing I don't know is my SF value. There, and there. Okay, so I have a quadratic equation there to be solved. So you could do this by hand. You could use the quadratic formula to pop that baby out. Or, I mean, I just put it in my calculator and worked it on out. And so that's what I would recommend for you to do. Just remember that whenever you get that number, whatever it is, before you enter it in Mastering Physics, you've got to add the original position of 0.6. Okay? Add that original position of 0.6. Okie dokie. There we go. Work and energy are pretty nice. They're very handy, very convenient to use. Okay?